Como quiso quizás no grabar para trabajar, para hacer en inglés. ¿Vale? Okay, good morning. I would like to, as director of IMPA, I would like to warm welcome our guests of the Executive Committee of the International Mathematical Union, and also to our colleagues and all of you present on this occasion. I would like to take advantage of this opportunity to say a few words about the IMPA and its structure and its importance. IMPA is about to be 53 years old, and since its foundation in 1952 has had its mission clearly defined by three items. The production of high-quality research in mathematics, the training of new researchers, and the dissemination of mathematics at all levels of knowledge by several means, including the elaboration of a national mathematical literature. We are 33 researchers covering areas like algebra and algebraic geometry, analysis, computer graphics, dynamical systems, differential geometry, fluid dynamics, mathematical economy, optimization, probability, partial differential equations. The scientific activities of IMPA are supported by a solid program of visitors and a high mobility of our researchers. The number of students in our master and doctoral programs is presently 189 and is increasing very fast during the years. Half of our students come from abroad, mainly from South American countries, and this accounts for an important presence of our graduates in Latin America, helping to disseminate the academic influence of IMPA. Each student at IMPA holds a fellowship from a government agency without regard to nationality. In its more than 50 years of existence, IMPA has helped to disseminate mathematics not only by means of graduate students, but also through the systematic elaboration of a right now very respectable national mathematical literature. In a developing country like Brazil, where support to science comes in reasonable amounts from the government, it is natural that special efforts be devoted to the search for young, talented people. We understand that this is fundamental for the development of the country, and especially in mathematics, in order to build a diversified leadership. After all, mathematics is so vast that the effort of many people will be necessary to establish a wide spectrum of mathematics in the country. IMPA is well aware of this need. For this reason, many projects are being developed devoted to the search for talented people for the scientific activities. The more recent is a remarkable project that will be launched next month by President Lula. It is a project of mathematic Olympiads for the public schools in the country. This project will be carried out by IMPA and the Brazilian Mathematical Society with the support of the government. It will involve the participation of at least 5 million students throughout the country, ranging in age from 10 to 16 years old. This unprecedented activity certainly will produce many talented young people that will be certainly followed by support to them. I hope that this information in this very short time would have given you an idea of the importance of the institution for this country and also for the region. In saying so, I wish to all of you a very fruitful meeting and stay at IMPA. Thank you.
So on behalf of the International Mathematical Union, I would like to say how much we appreciate being able to hold our executive committee meeting here at IMPA. So on Friday and Saturday, we took a lot of important decisions for the future of IMU. Only time will tell whether we took the right decisions, but we did our best. And then yesterday, after having worked hard for 2 days, thanks to the hospitality of Jacob and Suli, we were allowed to play hard for a day and swim hard. And this was, altogether, it's been a memorable stay in Rio. So thank you very much indeed.
Well, to conclude these words by the director and the president of IMU, I just want to say from my part as past president that it's always a great pleasure and an honor for us to have IMU here, and I'm sure this shall continue in the future. And so I'm sure that you're going to enjoy the remaining part of your stay. And thank you for coming. Okay, now we go to the workshop, properly speaking. And the first speaker will be John Ball. That's the title is over there. Also, he's from the University of Oxford, but he's Scottish in his heart, always.
Thank you very much, Jacob. So I'm going to talk about some open problems in the calculus of variations and elasticity. As you'll realize, practically every problem is open in this field. So here's the plan. I'll talk first of all about a mysterious convexity condition called quasi-convexity that plays a central role in the whole subject, but nobody really understands. Then about the sort of classical problem of the calculus variations, about necessary conditions for a certain function or mapping to be a local minimizer, and then turning these necessary conditions into sufficient conditions. Talk about the smoothness of minimizers. And these are all open problems, more or less completely open problems of the multidimensional calculus of variations. And then, depending on how much time I have, I will say something about dynamics, elastodynamics that is, and the morphology of microstructure in some materials, which has a relationship to these open problems. So let me begin with the setting. We have here a mapping Y that is going to take some region omega. It's a bounded domain, open connected set in Rn with some reasonably nice boundary, say a Lipschitz boundary. You see I've drawn part of the boundary in red here, and I've called it d omega 1. So d omega will stand for the whole boundary, d omega 1 for this red part. And so the unknown is going to be a mapping Y that takes omega to a possibly different dimensional space, Rm. So keep in mind that n is the dimension of the domain, and m is the dimension of the range. So the The important quantity is going to be the gradient of this mapping y, which at each point x you can identify with a real m by n matrix consisting of the partial derivatives of the components of y with respect to some Cartesian axes with respect to the components of x. So that way you get an m by n matrix, and m cross n is going to be my notation for real m by n matrices. Well, this is a little technical if you're not familiar with subless spaces, but usually I'm going to suppose that y belongs to the subless space W1p of maps from omega to Rm with p finite. This won't play a very big role in what I'm going to say, but for those of you who are familiar with such things, useful to know. So this space consists of mappings y such that this norm, which consists of the pth root of the pth power of y plus the pth power of the gradient, is finite, and the gradient has to be interpreted in some suitable weak or distributional sense. So this allows, for example, piecewise affine maps. They would belong to W1p. So what's the basic problem? It's to minimize an integral of this type. So we're integrating over our domain omega some function that depends on x and y of x and the gradient of y of x, subject to some suitable boundary conditions. For example, that we specify on the red part of the boundary what y is. It's equal to a given mapping y bar. And for simplicity, at least until I get on to the very last part of the talk, I'm going to always assume that f is smooth, the integrand is a smooth function of these arguments, and that it's bounded below. Well, when n, that's the dimension of the domain, is 1, and m, which is the dimension of the range, is bigger than or equal to 1, this problem is largely understood. So we're talking about in one space dimension, and there remain some open questions, but they're sort of details, really. And so the simplest case, of course, is when both dimensions are 1, and then we have this classical functional. Now the omega is just an interval, a, b, and we have a function f of 3 variables, x, y of x, and dy dx of x. Now when m is 1 and n is bigger than 1, this is a problem for a scalar unknown, but defined on Rn. This is also reasonably well understood, not quite so well understood. There are a few more open questions in this setting. However, when both dimensions are bigger than 1, the problem is much, much more difficult, and there are issues that arise that have no counterpart at all when one of the dimensions is equal to 1. And so this is the sort of situation I'm going to be discussing. And so in this case, almost every central question of the calculus of variations is open. Now, most of the difficulties are contained in the case when f just depends on the gradient. Because if it depends on x, you can sort of localize close to some point x, and then it's really not depending on x. And if it depends on y, then, well, by the fundamental theorem of calculus, y is the integral of the gradient, so to speak, so it depends better things depend better on y than they depend on the gradient of y, so you can handle that by some kind of compactness argument. So most of the difficulties are contained in this case, and so that's the case I'm often going to consider when I of y is just an integral of a function depending only on the gradient of y. And the energy functional of elasticity is of this type and is a main motivation for me and many other people. So then, of course, both dimensions are 3, and F is which I'll call C, is the free energy density of the material. So the fact that it depends on the gradient, it says that you're doing elasticity theory. Okay, quasi-convexity, what is this? Well, there's no real other way of introducing it but by giving the definition, which is very difficult to understand, even if you're an expert. In fact, nobody understands it. Well, they understand the definition, but they don't understand anything else, really, to speak of. So here's the definition. Right? So first of all, I'm going to take a matrix A, a fixed matrix A, and I'm going to tell you what it means for F to be quasi-convex at this matrix A. Okay, so this inequality has got to hold. Well, I'll come back to the inequality in a second. For all maps Z, which are smooth, and on the boundary are linear, Z of x equals AX. So that's the matrix A for all x in the boundary. Okay, so now, what is this inequality? Well, it's a kind of Jensen's inequality for gradients. So if we look at the left-hand side here, it's a functional of Z. Okay, now, the inequality says that a minimizer of this integral over here is given by the boundary data itself. Because, of course, if you put Z identically equal to AX, its gradient is A, and what you've got here is just putting dz equal to A. Now, of course, on the right-hand side here, you're now just integrating a constant. So it's equal to the measure of omega, the volume of omega, times f of A. Okay, so that's what the definition says, quasi-convexity at a matrix A. And f is quasi-convex if that holds for every A. Okay, so that's the definition. Now, the first thing that's puzzling about the definition is that this is supposed to be a definition about f and A, but also omega is in the definition. Right? So it looks as though the definition depends on omega. But it does not depend on omega. Okay? So that's a little kind of scaling calculation. It does not depend on omega. Okay, so that's the first remark. And it is, despite the fact that we don't understand it, we do understand that it's the central convexity condition of the calculus of variations. So I try and justify this a little. Well, first of all, if you make suitable growth hypotheses on f, then quasi-convexity of f is necessary and sufficient for this integral to satisfy the principal property, namely weak lower semi-continuity, to make the direct method of the calculus of variations work. So, it's necessary and sufficient for this integral to be sequentially weakly lower semi-continuous on this Sobolev space. And that implies that if f is quasi-convex, then this integral will attain a minimum subject to given boundary conditions. And this was first shown by Mori in 1952, and it was Mori who introduced this definition of quasi-convexity. And there have been many, many refinements of this since. So to make the direct method of the calculus of variations work by the usual sort of techniques, it's necessary and sufficient that f be quasi-convex. But perhaps the usual techniques are not the right techniques to use. But they are in some sense. So it's also necessary for the conclusion to hold. So it's necessary for the existence of an absolute minimizer if you are allowed to add an arbitrary smooth function of x and y. So in other words, if this functional attains a minimum subject to linear boundary data for any smooth non-negative of C, then f is quasi-convex. So more or less, it is quasi-convexity is necessary and sufficient for the existence of minimizers in the multidimensional calculus of variations. Here's another, this is what we were doing yesterday, by the way, but there's a different kind of relaxation here. So this is another illustration of how quasi-convexity plays a central role. Suppose you've got an arbitrary f. Okay, so then if it's arbitrary, more or less, certainly it is not quasi-convex. As you see, that's a bad thing. So we make it quasi-convex. How do you make it quasi-convex? Well, you take the supremum of all quasi-convex functions that are less than or equal to it. Okay? And you call that thing FQC, and it turns out that FQC is quasi-convex. Now, you can look at the two integrals. The first one, which is your original integral, and the second one, where you've replaced f by this quasi-convexification. Okay? And there's a very interesting relationship between these two integrals. So the second one is the relaxation of the first one. So for the first integral, our original integral, the minimum will in general not be attained. But you can take a minimizing sequence, so a sequence of maps that such that I of yj tends to the infimum of I subject to our boundary data. And so the theorem tells you that you can always extract a subsequence of such a minimizing sequence that converges, or technically it's weak convergence in this Sobolev space, it converges to a minimizer of the relaxed function. And conversely, any minimizer of the relaxed functional can be obtained in that way as the limit of a minimizing sequence for the original function. And the values of the infimum of the two functionals are the same. And of course, the infimum of the quasi-convexified function is in fact attained because the integrand is quasi-convex. Now, in elasticity, when F is psi, which is the free energy density, then psi QC has the following interpretation, that it's the macroscopic free energy function corresponding to the microscopic free energy function of psi. So we'll see more about this a bit later, but it turns out that for typical psi that occur in elasticity, there's a lot of microstructure, and the minimum is not attained according to elasticity, and there's a lot of microstructure, and so you predict that on the basis of this free energy function. But if you're standing at a level where you can't see this microstructure because it's a too small a scale, then you should use this quasi-convexified energy function. So quasi-convexification describes the passage from microscales to macroscales in materials. So that obviously poses the question about how, it's obviously a very important condition, how do we tell whether a given function is quasi-convex or not? Well, the first thing to do is to establish relationships between quasi-convexity and other convexity conditions, which are more easy to understand. So the first one is rank 1 convexity. So we say that F is rank 1 convex. If you look in the direction of a matrix of rank 1, so that a matrix of rank 1 is the tensor product of two vectors. So this is A tensor n is the matrix with coordinates A, I, and J. So if F is convex in such directions, so f of a plus ta tensor n is convex in T for every capital A and every little a and every little n, then F is said to be rank 1 convex. So this is actually related to strong ellipticity of the Euler-Lagrange equations for the function. So another convexity condition is called polyconvexity. So F is said to be polyconvex if you can write it as a convex function of all the minors of the matrix A. So J of A is the list of all minors of the matrix A. Minors are subdeterminants. So for example, if both dimensions were 3, then this list of minors consists of the 9 1-by-1 minors, the entries of the matrix A, the 9 2-by-2 minors, and the 1 3-by-3 minor, namely the determinant of A. So you have 19 variables here. So you say F is polyconvex if you can write it as a convex function of those 19 variables. And then we have these relationships between these convexity conditions. Well, F convex implies F polyconvex, which implies F quasi-convex, and it implies F, which implies F is rank 1 convex. So it's quasi-convexity is squeezed between polyconvexity and rank 1 convexity. But the converse implications are all false if both dimensions are bigger than 1, and these are all the same if one of the dimensions is equal to 1. Okay? With the exception that it's not known whether rank 1 convexity implies quasi-convexity when M is 2. Now, the fact that rank 1 convexity does not imply quasi-convexity in general, when n is bigger than 2, m is bigger equal to 3, this was a problem that was raised by Mori and solved sort of 40 years later by Vladimir Shverak in a famous counterexample. Well, here's a particular example which shows how little we understand about the subject. So here's a function of 2-by-2 matrices. Okay, so it depends on a real number gamma, which is this coefficient here. So now I'm using the Euclidean norm of matrices here. So sum of the squares of the entries, square root of. And this is therefore a homogeneous quartic polynomial in this 2-by-2 matrix A. And it is a fact that the range of gamma for which f gamma is quasi-convex is not known. What is known is the following, that f gamma is convex if the absolute value of gamma is less than this number. It's polyconvex if it's less than or equal to 1. It's quasi-convex if it's less than or equal to 1 plus epsilon for some epsilon. Unfortunately, we don't know what epsilon is, some positive epsilon. And it's rank 1 convex if it's less than or equal to this number, which is about 1.1547. And numerically, 1 plus epsilon is 1.1547. If you remember from the previous slide, it's not known whether rank 1 convexity is the same as quasi-convexity when both dimensions are 2. So this is sort of consistent with it being the same. It would be very important if it was the same. So here's the first open problem then. Is there a useful characterization of quasi-convexity? And here is a depressing piece of news that Jan Christensen has proved that in these dimensions, which are the same ones that the Spheric counterexample is based on, and it uses the Spheric counterexample actually, that there's no local condition equivalent to quasi-convexity. For example, no condition involving f and any number, say 10 billion, of its derivatives at an arbitrary matrix A. So that's very different from convexity or rank 1 convexity, which can be expressed in terms of such local conditions. That might make you think that there's no characterization at all. But also Christensen showed that if m and n are both big or equal to 2, there's no local characterization of polyconvexity. But polyconvexity is something one can understand. You know, you have to write it as a convex function of something or other. So possibly there might be a characterization. Perhaps somebody will come along with a really brilliant proof that some special functions were quasi-convex. And then these would include the minors, which both them and the negative are quasi-convex. And then maybe the characterization could be that f is the supremum of such a family. That would be a possible kind of characterization that would be consistent with this negative result. So a second problem I want to talk about is really the classical calculus variations, how the calculus variations was in the 18th and 19th centuries. So one of my favorite pieces of mathematics is this fundamental sufficiency theorem of the one-dimensional calculus variations, which is one time was very well known, but nowadays people don't seem to know it so much. So here's a statement of it. So first of all, we take a function in this case, because I'm doing the one-dimensional theory, y tilde, which I assume is C1 on this closed interval AB. So if it is a strong local minimizer of this integral with now I'm going to take some boundary conditions. So for sake of illustration, I'm going to take mixed boundary conditions where we specify what y is at A equal to a number alpha, and there's no boundary condition at B. So what happens at B is free. So what does it mean to be a strong local minimizer? That means that I of y is bigger or equal to I of y tilde for any y that's, say, C1, which satisfies the boundary data and which is close in the C0 or L infinity norm to y tilde, saying nothing about how close the derivatives of y are, the derivative of y is to the derivative of y tilde. Just the function has to be close. That's the meaning of this word strong, because you're requiring more than if you said, for example, that both y and its derivative had to be close to y tilde and the derivative of y tilde. So it's a stronger property to be a local minimizer in this sense here than if you specified something about the derivatives as well. So what are the necessary conditions to be a strong local minimizer? Well, first of all, we have the Euler-Lagrange equation, or vanishing of the first variation. So you take some smooth phi, which vanishes at A, and so therefore y tilde plus t phi satisfies the boundary conditions. This should be minimized at t equals 0, so the first derivative at t equals 0 should vanish. And so you get df dy times phi plus df dy dx times phi dx. This has to hold for all such functions phi. So that's the weak form of the Euler-Lagrange equation. And it's possible this derivative really does exist under my hypotheses, and it really does equal this. So the second necessary condition is because this is minimized at t equals 0, the second derivative at t equals 0 should be non-negative. So that's positivity of the second variation. Now, Weierstrass found another necessary condition, which was a sort of revolution at the time, and it says the following, that if you take any point in AB, then, and you freeze the arguments of f at x0 and the value of y tilde at x0, then this function of the last variable is convex at the derivative of y tilde at x0. So what does that mean? That means that this picture holds. So this is the graph of this function. Here is y tilde at x0, and the tangent to the graph at y tilde x0 must not lie above the graph. That's what this necessary condition says. The fundamental sufficiency theorem proved by Weierstrass and then given this brilliant proof by Hilbert, too brilliant a proof actually, but that suitably strengthened these necessary conditions are also sufficient. So for example, you replace N2 by a slight strengthening of the fact that this has to be bigger than or equal to 0. It has to be bigger than or equal to a positive constant times this integral. Okay? There's a slightly more subtle strengthening of the Weierstrass condition, but then the fundamental sufficiency theorem says that with these strengthenings, you get conditions which are sufficient to be a strong local minimizer. Now, for the multidimensional functional that we've got here, with the boundary conditions that I mentioned, I'm going to, the sort of natural or a natural generalization of strong local minimizer is to be a local minimizer in W1P for P finite. That is that I of y big equal to I of y tilde for all y with y equal to y bar on the boundary, and now y minus y tilde in W1P are sufficiently small. So here I do say something about the derivatives, but actually in the one-dimensional case, this will be equivalent to being a strong local minimizer. What I don't say is that the derivative of y has to be uniformly close to the derivative of y tilde. It only has to be close in the sense of LP. And then we have necessary conditions as before, the vanishing of the first variation. So we compute this derivative. Now it's, of course, a little bit more complicated because y is a vector and we have A as a matrix, of course, but exactly the same weak form has to hold for all smooth maps phi which vanish on d omega 1. And then the positivity of the second variation, that the second derivative with respect to t of this has to be non-negative for all such phi. So then the question is what the natural generalization of the Weierstrass necessary condition is. And there's a very obvious candidate for that. And that is quasi-convexity, which plays a role here. So first of all, let me explain what happens at an interior point x0 of omega. So this is a necessary condition that if you take a point x0, I freeze the value, the first two arguments at x0 and y tilde of x0, then it's a necessary condition that this be quasi-convex at the matrix dy tilde of x0. And that is actually, in one dimension, that's equivalent to the Weierstrass condition. However, there's something different that happens at a boundary point. A boundary point which is not on d omega 1, but on the free part of the boundary. And that's a condition called quasi-convexity at the boundary. And so what you imagine is that you blow up the boundary close to here, and then it will look like this. Okay, so it becomes flat because you've blown it up. So you take a domain like this, which has the same outward normal, and then it doesn't really matter what shape this red part of the boundary is. But so now you have a quasi-convexity kind of condition. You see the first two arguments on both sides are x1 and y tilde at x1. So x1, y tilde at x1. And then you have exactly the same kind of inequality as for quasi-convexity except that z now no longer has to be equal to dy tilde x1 times x on the whole of the boundary, but only on the red part of the boundary. And it's free on the black part of the boundary. So that's a necessary condition for y tilde to be a local minimizer in W1P. So therefore, a clear open problem is that could we slightly strengthen these necessary conditions so that they're sufficient? And if we did that, we would generalize the fundamental sufficiency theorem. Now, as you've seen, we don't really know how to verify, we wouldn't know how to verify the hypotheses of such a theorem. But it would have a very important sort of conceptual status, because it would tell, if we could prove such a theorem, it would tell us that we had not missed another necessary condition of the calculus of variation. So that would be the main, in our present state of knowledge, that would be the main advantage of proving such a theorem. Okay, now I come to the third topic, which is the regularity of minimizes. So the problem here is, I go back to the case when f just depends on the gradient of y, to ask, are there some reasonable conditions on f ensuring that absolute minimizers of this integral are smooth? In particular, is this the case for elasticity, when both dimensions are free under some reasonable conditions on the integrand, the free energy density? Well, here there's some very interesting lessons from the one-dimensional calculus of variations. So here's an old example of Vic Maisel and myself. So here's an integral of the calculus of variations. You see the interval is -1, 1, and we have here a polynomial in x and u and du dx. Okay, so there's a high power here, the 28th power du dx, but over here we have epsilon du dx squared. Epsilon is a strictly positive number. It has to be smaller than some epsilon 0 that's about 0.001. And the boundary data are that at -1, u has to be -1, and at 1, it has to be 1. Suppose you took this functional and you put it on a computer in the natural way to compute the minimizer. So you replaced an arbitrary function on -1, 1, satisfying these boundary conditions, by a piecewise affine function on some grid of mesh size h. For such a function, you can calculate this integral exactly, actually, because it's a polynomial, and you can minimize with respect to the nodal values, and you will get an approximate minimizer, hopefully, and you can do this for an extremely small mesh size, say 1/10 billion, for example, if you have an expensive computer. This is what would happen if you did that. The minimization procedure will converge. It will converge to two possible minimizers drawn here in blue. There's a reflection symmetry. That's why we get 2. You see it goes through -1, 1, 1, 1. They're smooth, perfectly smooth functions that satisfy the Euler-Lagrange equation. So that's the result of doing this finite element minimization for a very small mesh size h. So we have these two curves, u plus and u minus. However, those blue curves are not the minimizer of this integral. The real minimizer is another function, u star, which is not very well computed here. Maple, I didn't take a small enough mesh size, but it has an infinite derivative at the origin. It has a singularity which is like u star is mod x to the 2/3 sine x as x goes to 0. You can understand that if we go back to the functional. You see, that's what, imagine that epsilon was 0. If epsilon was 0, then an absolute minimizer of the functional would be exactly mod x to the 2/3 times sine x. What's very interesting here is, despite that you've perturbed this so that this function is strictly convex in du dx, this singularity remains. So now, in this case, du star dx is unbounded, and it does not satisfy the Euler-Lagrange equation. The Euler-Lagrange, the weak form of the Euler-Lagrange equation is equivalent to this integrated form in one dimension. Now note that this Euler-Lagrange equation is elliptic, since the second derivative with respect to du dx is bigger or equal to 2 epsilon. Epsilon is strictly positive. There's a theorem that says that any weak solution of an elliptic ordinary differential equation is smooth. Of course, there's no contradiction here because U star does not satisfy the weak form of the Euler-Lagrange equation. There is no theorem that says that even in one dimension with a smooth elliptic integrand, there is no theorem, it is not true that minimizers satisfy the Euler-Lagrange equation, even in weak form. Okay. Of course, there are theorems when you make other hypotheses on F which would assert that, but you have to make stronger hypotheses than are needed to prove the existence of minimizers. Now, moreover, as you saw actually from the computations, a remarkable phenomenon holds, the Lagrangian phenomenon, that the infimum of the integral among smooth functions is strictly bigger than the infimum among all functions. That's the only way in which one can understand the pictures that I drew. Of course, when you're doing finite element minimizations, you're effectively minimizing within smooth, or at least Lipschitz, functions. Now, that's almost, I mean, the first time I saw that, I just did not believe it, because, I mean, you could imagine taking this U star here and very close to the origin, replacing it by the linear interpolant between these values. Surely that must give you a value that's very close to the value of I for U star. Not a bit of it. In fact, if you do that for a very small, say, interval minus delta delta, and you let delta go to 0, then I of those functions U delta tends to infinity as delta goes to 0. So the numerical scheme is actually forced away from, or this numerical scheme is forced away from this minimizer. So moral, even in one dimension, absolute minimizers may not be smooth, and they may not satisfy the weak form of the Euler-Lagrange equation. You have to make additional hypotheses to ensure this. Well, now coming back to the multi-dimensional situation, where we've got an integral depending just on the gradient of y, what do we know about counterexamples to regularity? Well, in 1977, Nature produced an example where F was strictly convex even, and it had a global minimizer which was not smooth. So this is the ball unit ball. Now, because m is equal to n squared, you can think of y as being a matrix, and here is its ijth component. This is a map that is Lipschitz, but not C1. But on the boundary of the ball, of course, it's smooth. Okay? And it's the unique minimizer subject to its own smooth boundary data. So later, with collaborators, he managed to reduce n to n being bigger equal to 5. So this is then R5 to R25, provided that you change the y star a bit and the integrand a bit, of course. And then more recently, by more sophisticated methods, Schwerak and Jan found similar examples which work when n is 3 and m equals 5, or n equals 4, or m equals 3. But not, of course, m equals n equals 3, which is what we would really like. So we don't know what happens there. So what can we say? Well, there is a connection again with quasi-convexity. So here's a recent improvement of a classical theorem of Craig Evans, 1986. So if we strengthen the quasi-convexity condition somewhat, so instead of just saying that this integral on the left-hand side is non-negative, but saying it has to be non-negative in a certain way, bigger or equal to this kind of integral for some gamma and for all smooth functions. And if you suppose that f satisfies some extremely stringent growth conditions with the same power of a above and below, then any local minimizer y star of I is smooth outside some closed subset of omega with 0 n-dimensional measure. Actually, it was Mori who first proved a partial regularity theory for PDE of this type. And there are remarkable counterexamples that show that this is false if you just suppose that y star is a weak solution of the Euler-Lagrange equation. So assuming that it's a local minimizer gives you much extra information. So summary, in elasticity, and in elasticity I should say that if C is not a smooth function of A, it blows up as the determinant of A goes to 0, we'll need to use, if it's indeed true that you have a regularity, we'll need to use some special features of the problem. One may be low dimensions, there's sort of frame indifference, which is rotational invariance of the energy function and so on, but it's a completely open problem. Okay, well, I have 5 minutes to say something about elastodynamics and microstructure morphology. So let me talk about the first, perhaps the easiest kind of dynamics that one might think that one could handle, which would be viscoelasticity of rate type. So now we have y going from omega in R3 to R3, but also it's going to depend on time t. And so here's the PDE of viscoelasticity of rate type. So we have the acceleration here is equal to the divergence of the stress. The stress is given by differentiating the free energy function with respect to its argument, which is this matrix A. And then you have, so inside the divergence also, you have a function which depends on the deformation gradient and the gradient of the velocity. Now, in order for this to be frame indifferent, so you can use the same equation if you're measuring all the quantities. You're sitting on a moving roundabout or something, or an accelerating moving roundabout. You get the same equation, but with different quantities. Then S has to satisfy this condition that it is equal to dy times S of u and du dt, and u is the strain matrix. It's the square root of dy transposed times dy, which is a very messy object to use indeed. Now, when S is 0, so that's when you've got no viscoelastic term, that's just the equations of pure elastodynamics. That is, at the present time, is completely intractable. It's a multidimensional system of conservation laws. We only know things, any sort of rigorous things about such systems in one space dimension, and even that is very difficult. So you might say, well, let's take the simplest possible viscoelastic case you could. So let's take S equal a constant times the derivative of dy dt. Then the equation would look like this. So this term here would be mu times the Laplacian of dy dt. And that's actually a well-posed equation, because you can take this over the left-hand side, and you see it's the heat operator acting on dy dt. You can then invert the heat operator on this thing, and the heat operator is so good that it kills all the nasty things that are in here. And you can get a theory of such an equation, but it's not frame indifferent. It does not satisfy the frame indifference condition that I put before, and as far as I'm aware, there is no theory that applies to a frame indifferent version of this equation. One particular situation in which we encounter a lot of these problems about dynamics and quasi-convexity concerns microstructure morphology. So microstructure in solids is typically due to solid phase transformations, which involve a change of shape in the crystal lattice at some critical temperature. And it's very, very important because the microstructure morphology determines the macroscopic properties of the material. So here's a particular example. This is a high-resolution electron micrograph of nickel manganese, and you can, each dot is an atom, more or less, or a row of atoms perpendicular to the screen. You see you have a microstructure in which the deformation is piecewise affine in layers which are about alternately 10 and 6 atomic spacings wide. And if you look very carefully, which I won't give you time to do, you'll see this is a cubic to tetragonal transformation. If you look at the atoms, you see that on either side of one of these interfaces, in these are the cubic axes, you see there's been a kind of extension in one direction, which is now tetragonal, and on this side it's been extended in the other direction. And that's how these boundaries are to be understood. Well, there's an elasticity model for this, which in statics would involve minimizing a free energy of the function of the type that we've discussed already, but now we have a dependence of the temperature in there. And there's a certain energy well structure. I don't think I've got time to describe it, but there's an energy well structure, something we assume about what the set of minimizing deformation gradients is. So this is what it is for a cubic to tetragonal transformation. I don't think I will attempt to describe it, but there is some kind of hypothesis that attempts to put into the continuum theory what's happening at the microscopic level. Well, what is interesting, however, is that this energy function is not quasi-convex if it's going to predict phase transformations. And so in general, the minimum is not attained. And that's how this very fine microstructure is predicted according to this model. You think of it as if it's trying to minimize the energy. You take a minimizing sequence, and dyj, this set of deformation gradients, converges weakly, so but not strongly, so that you get this theory will predict an infinitely fine microstructure in the limit as j goes to infinity. If you put in some interfacial energy, then the model would then predict a length scale for the microstructure. But with no such interfacial energy, which is in any case very small, an infinitely fine microstructure is predicted. This is a picture of how it goes from the high temperature phase, which is cubic, so it's a constant deformation gradient over here, to tetragonal, where you see one of these fine laminates. So this is the way in which you go from the high temperature phase to the low temperature phase. So at high temperature it's cubic, at low temperature it's tetragonal. It has to do this by this very fine laminate. These sorts of plates here are nucleated at different points of the material. And then they come crashing together in a very interesting process, which is not very well understood. And so eventually the high temperature phase is eliminated, and you get features like this, where two of these martensitic laminates come together along some other kind of interface. In other materials, this is a copper zinc aluminum, a shape memory alloy. You get much more complicated pictures in which there appears to be sort of fractal structures. It's very difficult to know how to interpret these pictures, but loosely speaking, in each sort of band with a different color, there's a constant deformation gradient. Here are other pictures in different shape memory alloys, copper, aluminum, nickel. Again, these are now optical, the last one, and these are optical micrographs. So again, in each kind of region, you have a constant deformation gradient. You can think of this as being a minimizing sequence, and you get interesting detail near some kinds of interfaces. So up to now, attempts to understand this microstructure morphology have just used statics, and they're not really truly predictive. There's lots of different energy minimizers. We don't know which one is really relevant. And in some sense, the answer is put in at the beginning. You look at one of these pictures. You say, well, can I rationalize this particular geometry in terms of the theory? And then you get some very interesting details and new predictions, but you don't really say why you see one particular microstructure rather than another. And so that's a big open problem. It's clearly a pattern formation problem. It clearly requires an understanding of what the appropriate dynamic model is. At the moment, I mean, if you had such a model, then you should be able to wheel in and you could analyze it in some sense. You should be able to wheel in the apparatus of dynamical systems theory, infinite dimensional dynamical systems theory. You could look at invariant manifolds, attractors, and so on. And that way, you would hope to be able to say which of the features of these microstructures that you see are predictable, that you would get when you repeated a given experiment, and which are not predictable, and which might change from one realization of the experiment to another. But we don't really know what the appropriate dynamical equations are, and we're a very long way from handling either analytically or computationally any such possible candidate for a model. So if you're interested in some of these problems, you can download, this was written about 2 years ago, a survey article which is on my webpage. Thank you.
Thank you
this very comprehensive picture of this subject. Any question or comment? If not, then let's thank the. Oh, I got a crazy question.
Is there any area besides elasticity? I'm not sure I want to use this. Any area where you would have similar problems of minimizing existence and smoothness of minimizers and things of that kind that is totally unrelated to elasticity. I understand this is the natural one from many points of view. Is there any
In which sort of quasi-convexity and so on play a role similarly? Or, yeah.
Well, you wouldn't mention the word elasticity at all.
Yes. Well, I mean, this theory I've described is very similar to homogenization in some sense. Whenever you have a homogenization problem or an optimal design problem, a lot of these similar issues arise. I mean, here the material is in some sense homogenizing itself, whereas in many sort of applications you're talking about sort of man-made or nature-made heterogeneous materials. So I think that would be the main analogy where these similar issues arise. But I mean, there's all sorts of other theories of mechanics, say liquid crystals and so on, where similar questions might arise. It's all dependent on what the particular models are that people think of as being successful. But in sort of liquid crystals, you get all these disinclination singularities, which are terribly important for liquid crystal displays and so on. I mean, I think that because it's such a fundamental condition, it should play a role in many areas where we don't know. And one I would guess would be sort of topology in some sense. I mean, because, for example, topological invariants, like the degree of a map, are defined in terms of null Lagrangians, which are these minors. So you'd think that in terms of topological invariants, maybe quasi-convexity should have some bearing. But then these different communities, of course, don't know how to talk to each other.
Okay, so let's thank the speaker again. And we'll be here again, say 11, 10 minutes for coffee, the coffee from